let's start today's tutorial. Um, so in today's tutorial, we have to show that for monochromatic waves, for non-monochromatic waves, this transition probability um, 2 over epsilon naught rho of omega sine square omega ba minus omega times t over 2 over omega ba minus omega square. So we have to solve this integral for non-monochromatic waves. So let's see how we can do this integration. So this is b from a to b. Let's take all the constants out of the integration. So 2 dab over epsilon naught h bar square, so 0 to infinity d times omega, d of omega, rho of omega, and sin omega ba minus omega t over ba minus omega square. Okay, so this term will give us the broad spectrum, and while this term will give us the sharp peak about omega equals omega ba. So we have to draw these or both of these. So here, so let me call this function y. So here's omega and here's the rho of omega. So this will just give you a sharp broad peak. And for the case of this, if on this axis I have omega, and on this axis I have this function y, this whole function sine square over of the argument. So this will give me that our wave is peaked around this this frequency, that is omega equals omega b. So let's see how to proceed further. We can employ a very important trigonometric property of sine function, but to employ that property, we have to convert this integration from zero to infinity, from minus infinity to plus infinity rather than 0 to infinity. So we know that so I can write this 0 to infinity d omega sine square omega ba minus omega times t over 2 over omega ba minus omega square approximately when equals to minus infinity to plus infinity. So d omega and this whole argument. So now this term can also be separated into two integrals. So minus infinity to 0 d omega something plus 0 to omega d omega and this something. Now we can easily see that this integral, according to our spectrum, um, this integrand is close to 0 for omega from 0 to infinity. So once we plot it, we can so this can easily figure out. Now we can set the argument equals to x. So we have changed the limit. Now we are replacing the argument with this factor x, and dw will be minus 2 over t dx. Now now my integral will become minus infinity to plus infinity d of omega sine square omega b of minus omega t over 2 omega b minus omega square equals minus infinity to plus infinity. Let's substitute all the variables that we have calculated on last slide. So this will be minus 2 by t dx, and the argument will just become sine square x over 2x square over t square. So by keeping all the constants out of the integral, 2 over t minus infinity to plus infinity dx sine square x over x square. Okay. Now this term, to solve this term, we will use the identity. So this term will turn out to be equals to pi. Okay. So now equation number 1, that is our starting equation, will become a to b as a function of t to d ab over epsilon naught h bar square of omega ba or ab pi t by 2. So this is this is the answer to the this is the solution to the integral that we have to calculate. Okay. Now from this we can also calculate transition rate. So the transition rate can be defined as dt. So by dividing equation number t with equation number 1 with t will give us r a to b. So r a to b, sorry, pi d epsilon naught over epsilon naught h bar square rho of. So this is the transition rate which is independent of time, so which is constant on time. Okay, so far we have considered that the perturbing wave is coming in along while coming in along specific axis, the y-axis, and the perturbation is along, and the polarization is along y-axis. So, but what if we want to consider all of the possible type of polarization, or we can say that atom is just bathed in all types of radiation from all directions, and we want to calculate or we want to include the polarization randomness in the incident light. So we have to average over different epsilons. Now we can see how we can do this calculation. Now we need to take into account polarization randomness, and incident light. Because so far we have only assumed that same. So perturbing wave along y-axis is coming in along y-axis, polarization along z-axis. But to answer this thing, we have to average over different epsilons. Okay, so if I have to draw, if I have to draw the, if I have to draw the diagram for the previous case, then it will simply be like this. So how can I average it over different directions? This is my coordinate axis. This is x. This is y. This is z. And in this direction, I have d, b, a. And this is the epsilon hat when angle theta with this axis, and the y component. Sorry, and the phi component is this phi. So this can be a guiding diagram. So we now just have to average over different epsilons. And to average over different epsilons, we can rewrite the transition rate as pi over epsilon naught h bar square d ba epsilon hat square. Let me call this equation number 2. So let's calculate what this term is. So since we know that d of ba dba cos of theta by taking the square, this will be d of ba square cos square theta. Now we have to average this. So to average this, we can write this 4 pi 0 to pi d theta 0 to 2 pi d phi dba square cos square theta sin theta. Okay, so while this vector shows that we averaged it over the complete solid angle by rigid solid angle. Okay, so calculate by solving this integration, I can get dba 1 over 4 pi 0 to phi. I will get 2 pi by integrating over theta and keeping this constant out of the integral, and by integrating over theta, just retain with this term d theta cosine square theta sin theta. So this is 1 over 2 db square by integrating this minus 1 over 3 cos 3 theta 0 to pi. This will give me dba 1 over 3 dba square. Now by this equation, let me call this equation number 2, this equation will become RAB pi over 3 epsilon of h bar square dBA square, and the retaining factor of spectral RBA. Okay. As a factor 3 will show that we have taken a random polarization. So the factor 3 shows the randomness in polarization. Okay, so that's it from this tutorial, and I upload a tutorial on blackbody radiation soon, probably this by this Sunday. Thank you.